this video is about half-life. Now, a lot of the classes I have get really confused as to what half-life actually is. It isn't as complicated as what it seems. So to understand it, you need to understand basic radioactive decay. So as all radioactive atoms decay, fewer and fewer radioactive nuclei will remain, or that means that the activity rate of that atom will drop, okay? So it's not giving out as much radiation. Now, radioactive decay is a random process, and this happens when radioactive isotopes want to be at a lower energy level, so they do this by emitting alpha, beta and gamma. So it's a random process. An isotope, if you can't remember, are elements with the same number of protons but different number of neutrons. So it affects their physical features. It doesn't affect their chemical properties, only its physical. So there's two definitions of half-life, and either is acceptable in the exam, and they do quite often ask for you to write it out. So it's either the average time taken for half of the radioactive nuclei of an isotope in a sample to decay. So the average time. Now the reason why it's an average is because even if you have two isotopes which are identical, they're not necessarily going to decay at the same rate because of it being a random process. Or the other definition is the average time taken for the activity count to fall to half of its starting level, and that's usually when they've given you a graph and stuff. So this is one of these graphs that looks more complicated than it actually is. Activity is just how much radiation they're giving out, okay? And then the time will either be seconds, years, minutes. It depends on the isotope. But if the exam question for this one said, what is this isotope's half-life, you always go to the starting level, then go to half of the starting level, go across to where it meets the line, and then read down. Now be careful because they can be a little bit tricky with these. They'll make it a tiny little square that you have to put the specific amount that it is. So here would be about 18 years. Now the thing about half-life is, so it's 18 years to get to half of its amount, but it is also then another 18 years to get to half of that, so to get to a quarter basically. And then it would be another 18 years to get to an eighth, and then another 18 years to get to a 16th, which is why this graph doesn't actually go down to zero really, because it will always just half and half and half for that amount of time. So also in exam questions I have seen them say this isotope starting count was 2000, and it then used 80% or dropped to 80% of its activity rate. How much time would that take? So it used 80% activity. So you then have to look at, okay, so what is 20% you've got left? What is that on the graph? So you'd read it from the graph and then go along, okay? Other ones will actually get you to work out from information. So for example, if you have a look here, now you can pause this and try it, but I'll just explain the first one. If the half-life of this isotope is 20 years and 60 years has passed, it then wants you to work out how much would be remaining. Okay, so if you had 1,000 count rate to start with, 20 years plus 20 years is 40 years. So after that time, half of this is going to be remaining, so that would be 500. Another 20 years, which would then bring you up to 60 years, means you'd have half of that, so it would be 250. So if you want to try the remaining 3 and pause it, I'm going to go on to the answers for the other ones. So as you see here, if the half-life was 5 minutes and it had been 5 minutes, from 1,000 it would drop to 500. If the half-life was 6 months and it had been a year, well, 6 months and 6 months means it's been 2. So the first 6 months it dropped to 500. The second 6 months, so a year, it would then drop to a quarter or 250. If the half-life was 30 seconds, so 30 seconds, it would then be 500. After another 30 seconds for a minute, it would be 250. Then after another 30 seconds, so 1.5 minutes, it would then be 125. So it's just a case of just working out basically how many of those half-lives have occurred in that space of time that's been given to you. So different isotopes have different half-lives. None of them are the same. Some can be like milliseconds, others can be billions of years. The plutonium that's left at Chernobyl, for example, has got a half-life of 24,000 years. But they can vary. Scientists can use them in different ways. They can use them to carbon date. Have you ever heard of that? It's carbon-14, because normal carbon, of course, is carbon-12. So we can use carbon-14 to actually date objects that we find. And you can also use them as medical tracers and things like that. But medical tracers, you'd kind of want them to have a very short half-life, so it's not going to be that radioactive in the patient for very long. So don't make it more complicated than it is, and I hope that helped.